We've got Ben Devenish from the Met Office and Imperial College, who's going to be talking about machine learning for atmospheric.
I'd like to start by thanking the organisers for the invitation to speak at this event. So my name is Ben Devenish. I'm part of the Atmospheric Dispersion and Air Quality group at the Met Office. I also have a visiting position at Imperial College. As a group, we're fairly new to machine learning. So the examples I'm going to show you this afternoon are small-scale, largely scoping studies. The exception to this is Bayesian inversion modelling for volcanic ash. It's not really machine learning, but I thought as it's a Bayesian model, it would be of interest. And that is now, it can be run operationally by the Met Office. And I'll also talk briefly about generative diffusion models later on. The examples are quite specific. They relate to pollen, air quality, urban dispersion. The generative diffusion models is more generic. I'll start with an overview of the Met Office's dispersion model, which is known as NAME. It was originally developed after the Chernobyl accident in 1986, when the acronym stood for Nuclear Accident Model. People liked the acronym, so they kept the acronym and just changed the meaning of it. And when it was originally developed, it was originally developed as a Lagrangian model. It's now become a hybrid Lagrangian-Eulerian model, and I'll talk more about both of these later, explain what the two terms mean. It's important to note that NAME doesn't calculate the flow field. The flow field comes from the weather forecasting model, the numerical weather prediction model. So there's often these sorts of models that read in the flow field at arbitrary but fixed time intervals are often referred to as offline models. And then we calculate the dispersion through that flow field. It's now widely used, not just for radiological species, though it's still used for radioactive species. Probably the most celebrated event was the eruption of Eyjafjallajokull in 2010, and this model was the model that was used to make predictions. I'll come back to that particular eruption and show you some examples of what we did. It's used for air quality modelling. It includes atmospheric chemistry. It's used for the dispersion of pollen, which I'll talk about more. It's used for dispersion of Saharan dust. It's also used for a wide range of biological species. Viruses such as the foot and mouth virus, which is unusual among viruses because it remains virulent over long distances. Disease vectors like midges, which carry blue tongue disease, and other biological species like the wheat rust spores, which can do a lot of damage, particularly in areas like the Horn of Africa, and similarly locusts. And sort of what I've referred to so far, I'm assuming that the properties of the source are known, its location, the emissions, and so you can run the model forwards in time to predict where that material is going to go to. But it can also be run backwards in time, not like running a film backwards in time, but if you have a receptor measuring material and you'd like to know where does that material come from, then you can run the model backwards. And this is very useful for greenhouse gas attribution and also for detecting the sources of illegal CFCs. So I'll start by talking a little bit about the weather forecasting model. And this is key to realistic, accurate dispersion modeling. And the Met Office has various configurations of its NWP model. It has a global model, which it runs 4 times a day. And then it has a high-resolution model over Britain, which I think is run every hour. And the spatial grid spacing of the global model is about 10 kilometers at mid-latitudes, whereas the UK model is about 1.5 kilometers. And the global model then is used to create boundary conditions for the UK models. As you can imagine, even 1 kilometer spacing, 1.5 kilometer spacing, a lot of physics is taking place below the grid scale, and that's even more the case for a 10 kilometer grid spacing. And so a lot of what NAME does is to provide a subgrid representation of the physics at below the grid scale. And as I said, we have two two configurations of the name model, Lagrangian and Eulerian. So a Lagrangian model is, if you imagine you're sitting on a tire, a rubber tire dinghy floating downstream, measuring the properties of the stream as you float downstream, that would be a Lagrangian model. And similarly, in the atmosphere here, in our model, we're tracking notional particles from a source through the atmosphere. And one of the advantages of this approach is that subgrid scale sources, which includes a lot of sources, most sources are smaller than a kilometre scale, certainly 10 kilometre scale, are very easy to represent with a Lagrangian model. And so you can capture the near source behaviour, particularly when the plumes are narrow. They've also been very successful in modelling convective boundary layers. Convective boundary layers characterised by narrow but strong updrafts and then large, slowly descending air masses around those updrafts. But they can be expensive, and of course the cost increases with the number of particles, but the noise only decreases like 1 over the square root of the number of particles. And with the Lagrangian model, you don't get the concentration directly. You have to specify an arbitrary grid, which isn't necessarily the same as the computational grid, and then you sum up the mass on the particles to get the concentration. An Eulerian model, on the other hand, solves the scalar transport equation and solves directly for the concentration. And this is much better suited for problems where you've got slowly varying species that might occupy a large spatial extent. And this is particularly the case for air quality modelling. And they're also advantageous when you have many different species, which is also the case with air quality modelling. In a particle model, you would need to ensure that you have enough particles to represent all your different chemical species. But they also can be problematic. You need to define a grid on which you solve the equations, and that grid is typically the same as the same resolution as the flow field that comes from the weather forecasting model. So that's cut coarse. So that introduces numerical diffusion, and it's also very difficult. It's also very difficult to represent subgrid scale sources because the minimum size of your source has to be one computational grid cell. But in name now we can run as either a Lagrangian model or an Eulerian model, or we can run it in a hybrid mode where we release material on particles, then after some specified time we transfer the material from the particles to the field. So this gives you a sort of intuitive feel for what the Lagrangian model is doing. Here on the left is a volcano, and you can imagine sort of tracking random particles through the flow that come from the source of the volcano. And the motion of these particles is the sum of the flow field that comes from the weather forecasting model, which is just interpolated to the particle's position, plus a random increment that accounts for the subgrid scale processes, particularly the turbulent eddies that the weather forecasting model is not resolving. So again, here this illustrates what the effect of adding subgrid scale noise, random increment to your particle's position. If you release particles from the same source without any turbulent, without any random increments, all the particles would then just follow the same trajectory, and you'd get no spread. If you add random increment to the particle's evolution, so you're adding a different random increment at every time step to each particle. Each particle is released, although they're being released from the same source, they're all travelling independently. Here you can see the effect that as you add the random increment, you get spread downwind from the source. And this isn't just occurring in the horizontal; it is also occurring in the vertical too. So it's representing the vertical diffusion, horizontal diffusion that you would get as a result of the unresolved turbulent eddies. So how do we apply that random increment? We have two different levels of stochastic differential equations. The first is where we just apply the random increment to the particle's position. So this is equivalent to just a simple diffusion equation that's spreading material through space. And there the size of the random increment just depends on the size of the diffusivity. And then we also have a high level of stochastic differential equation where we apply the random increment to the particle's velocity. And here the size of the random increment depends on the velocity variance and the decorrelation timescale. So this reduces to the Langevin equation in homogeneous turbulence, which you may have come across. And here you can see there's a term proportional to velocity over the decorrelation timescale. And this ensures that the particle never travels too far from the mean. So these sorts of processes are often called mean reverting processes. But in inhomogeneous turbulence, you need to account for an acceleration, which is because the variance here depends on position, and so you'll get a non-zero derivative, and that occurs in this term here. And you need to construct these equations in such a way that if you release a uniformly distributed cloud of material, then that stays uniform, because you don't want any spurious unmixing in your simulations. And the reason we have these two equations is because close to the source, this first equation here doesn't give the correct shape of the cloud. Okay, well, there seems to be a slide missing, but from this equation you can derive limiting solutions either at short times or large times, and so this is your source. It's spreading out like this. Then the simple diffusion equation would just give you a parabolic spread. When you apply the Langevin type equation, would give you a straight line, at least up to times of order the decorrelation timescale, after which it then behaves like the parabolic cloud. And this was the result actually derived by G.I. Taylor, who was a fluids dynamicist here in Cambridge, without any reference to random walk models. So that's why we have two levels of stochastic differential equations, because if you want accurate information close to the source, then you need to use the second one. But this is more expensive because you then need to integrate it again to get the particle's position. So I thought I'd start by illustrating some of the examples I'm going to talk about with perhaps the most celebrated use of our model, which was the eruption of Eyjafjallajokull in 2010, which caused an enormous amount of disruption. And then, of course, it was this model that was used to make the predictions of the ash cloud. We received a lot of criticism at the time, and some of which we've addressed, and some of which I'll talk about in a moment. But I thought I'd start by showing you a video of the model versus satellite observation. So this was for a period in the eruption, I think in early May. What was unusual about the eruption was, or one of the things that was unusual was that it lasted 5 weeks, and there were some distinct phases, one of which was early May. So if you try and keep an eye on both of these, you've got the satellite satellite observations on the left and the model here on the right. I like to think that the model does a reasonable job of capturing the satellite observations. Okay, I'll move on. So what? Okay, so the slides got swapped around. So one of the things we were criticised for at the time was not making use of observations. So since then, we've put a lot of effort into, first of all, identifying ash in satellite observations and then using it to reconstruct the source. So what we want to know is how much material is released by the volcano. So that's of course, one of the key things in trying to quantify downwind dispersion of volcanic ash. I mean, up until 2010, the advice to airlines had always been to fly around volcanic ash clouds, and that works in most parts of the world. But in a densely populated part of the world like Northern Europe, that was no longer sufficient. And the airlines very quickly wanted to know what the concentration was of the ash in the cloud. And that's a much harder problem to answer because you have to have some idea of what's released by the volcano, most of which falls out close to the source. So you need to have some idea of what fraction survives into the far field, and also what the size of the particles. And it's mostly, of course, the smaller particles that survive into the far field, and they're the ones that do the most damage to the jet engines. So one thing we've done is use Bayesian methods to reconstruct the source, to alter to determine how much is released and at what height. So most of you are probably familiar with Bayes' equation. What we're aiming for here is to estimate the posterior, and it's related to, it's proportional to the likelihood and a prior. In this case, we don't take the evidence into account. The evidence is very expensive to compute, and it's not changing. As a prior, we use an empirical relationship between the rise height of the plume and the emission, and so the relationship to the rise height of the plume and what's released by the volcano. If you don't have much in the way of observations, then the prior will dominate, and then of course, if you have good quality observations, they will give you a better estimate of the source than the prior. And we applied this to another eruption. That's the eruption of Grimsvötn, which occurred the following year. And on the left here, you can see this is the emission that the prior would give. This is the empirical relationship between the rise height and the mass flux. And here you can see this is the output from the dispersion model at some point downwind. And here this red contour here shows the outline from the satellite measurements. So you can see it's greatly the extent of the ash cloud, as just using the prior, is vastly overestimating the ash cloud. When you apply the Bayesian inversion modeling, so we have a much both lower source and less powerful, and you can see that the result is something that's much closer to the satellite measurements, although there's still some positional errors, which due to errors in the meteorology. And because we have errors in the meteorology, we can go further than just using the deterministic forecast, which you then you just take the optimal value from the posterior. We can use an ensemble of forecasts and select the best of those forecasts. And we do this in a couple of different ways, one of which is in minimizing the cost function, and another one is in maximizing the evidence. So here in the top line is the prior I showed you just now, and the dispersion modeling that resulted from that. And these are two different ways, using an ensemble of meteorological forecasts with two different ways of selecting the best member. And you can see that both of those do a better job closer to the satellite measurements. So the next example I'm going to show you, which is more in keeping with machine learning, is dispersion of pollen. Met Office has a commitment to issuing pollen forecasts, and for that we need to have some idea of how much pollen is released. And because trees have a masting cycle, the amount of pollen that's released varies significantly from one year to the next, and often that cycle is biennial. So a masting cycle is where a tree produces more fruit than is used by its predators. I think the biological reason for this is so that the tree can then go on to reproduce. And this is difficult to estimate in advance. But we're going to use a number of different machine learning techniques to see whether we can get an estimate of this year's pollen release based on the previous year's meteorology. So here you can see the variation in the amount of pollen release. This is from a number of different measuring sites. And you can see there's often a biennial structure, but even then it varies significantly from one year to the next. And so we're going to try a number of different techniques. And I should say that most of this work has been done by other people. This in particular was done by Lucy Neal at the Met Office, and she took as feature data meteorology for the previous year. So the release in the pollen in the spring depends quite significantly on the meteorology of the previous summer. So she took various different meteorological fields: temperature, relative humidity, precipitation, wind shear, and this quantity APIN, which is the integrated amount of pollen in each year. And she took that over a number of years. So here you can see the relationship between monthly temperature, mean temperature, and the integrated pollen from the previous year. There's quite a large scatter. She applied the various different models: random forest, gradient boosting, and NMLP regressor. Separated the data, used 80% for training and then 20% for testing, and found that the gradient boosting regressor gave the best results. So here you can see this was the training data, and this was the test data. The target data here, of course, is the amount of pollen released in 1 year, and so you're comparing your prediction with target data of the pollen released 1 year, and then with using the meteorology of the previous year. So the next example I'm going to look at is using machine learning for air quality modeling. So again, to be two different aspects of air quality modeling. First is to look at whether machine learning can improve emissions. So this particular machine learning model used the observations to populate a 1 kilometre grid output over England. So for these species here, so ozone, nitrogen oxides, sulfur dioxide, and particulates. It was a very fast model to train. It took only 1 to 2 hours, and then could complete a pollution map of England in just a few seconds on very ordinary platforms. The feature vectors that were used in this were meteorology, land use, transport infrastructure, and of course the emissions themselves. And this was work done by Helen Buttery at the Met Office and Liam Beresford at Exeter University. Here you can see a comparison of the machine learning model with another air quality model at the Met Office. This is an Eulerian model that's embedded within the NWP model. And this has a much coarser resolution. The resolution of this model is about 12 kilometers compared with the 1 kilometer machine learning model. You can see there's much more detail here, where the information has been spread out in the physical model. And they found that the machine learning model was very good at capturing extreme events, particularly of nitrogen oxides, because it was applying a much higher resolution. It wasn't spreading the limited number of observations of sources over large areas as the physical model is doing. But it turned out it wasn't so good at predicting extreme events of ozone or particulates. And the reason for this is probably because the machine learning model doesn't do any advection. Each pixel is independent of the neighboring pixels, and ozone and particulates they travel over long distances, occupy a large spatial extent. And they also applied machine learning to post-processing. A lot of what you actually get, what you see on public forecasts will have had some post-processing. And we found that machine learning could do, so this post-processing is primarily there to remove biases in the model. And the machine learning model was applied to see whether they could do a better job than the conventional means by which the biases are removed. And here you can see that once the processing has been applied, they get closer, results closer to the one-to-one line between observations and model. I've got two more things I want to talk about. Okay. So I'll just talk briefly about generative diffusion models. So this isn't with any particular application in mind. We're interested in, one of the things we're interested in doing, we want to do more probabilistic forecasting in order to quantify uncertainty. We need methods for generating, cheap methods for generating more trajectories. And a generative diffusion model seems to offer for that possibility. It's been widely applied to image processing, so the idea is that you gradually denoise an image, and then the model learns to reconstruct it. So I think the idea is that you can start from a simple distribution that is straightforward to sample, and then you're aiming to sample a much more complicated distribution. So it's not unlike MCMC methods, but the idea is to use variational inference that we heard about this morning. So you can start with a simple distribution and gradually iterate towards your desired distribution. And you're aiming to get as close to that as possible, and what's meant by close is quantified by the Kullback-Leibler divergence that we heard about this morning. Once you can do that, you're able to recreate your image, or you're able to recreate your trajectory. And this idea has been applied to homogeneous isotropic turbulence. And I've taken the same code and applied it to a convective atmospheric boundary layer. So we have a point source in a typical sort of summer afternoon flow field, taking the flow field from an NWP model, and then used name to provide the training data. And these are the sorts of trajectories that it comes up with. Here we have wind speed and direction. And you can see here is the vertical velocity and height. And you can see this is a typical looping behavior that you find. It's very typical of convective boundary layers, where you have, as I said earlier, you have small narrow updrafts and large downdrafts. And material can be brought up, taken up from the sources, as well as spread horizontally downwind. And the final thing I want to mention is collaboration with colleagues at Imperial College, who have been looking at developing very high resolution flow fields for urban flows. And one thing we can't do at the moment is street scale dispersion modeling, and that's something that we'd like to be able to do. And of course, it's far too expensive for an NWP model to do, but we would like to use high resolution models, perhaps ultimately from large eddy simulation, to build machine learning models, which we can then use for dispersion modeling, just adding a simple scalar and tracking it through a flow field. So a lot of what we do is characterizing and quantifying sources. So for example, the pollen example I showed you as an example of that. Also the air quality, the first of the two air quality examples I showed you, where we want to quantify emissions. Other things that we do are post-processing, again, that's particularly of air quality models. And where we think machine learning could be very beneficial is in providing much higher resolution flow fields, much more detailed information than is currently the case. And we think one example where that could be useful is in street scale dispersion modeling. Finish there.
Great. Thanks, Ben. Does anyone have any questions following Ben's presentation? And if you could introduce yourself as well.
It's Laura from the University of Oxford. I had a question about the main. So you have your stochastic turbulence, but I wondered if the initial conditions of the wind field, the uncertainty that comes from that as well.
Yes, and we do run dispersion problems taking an ensemble of different meteorological forecasts, and that would give you a way of quantifying at least some of the uncertainty. I mean, what we don't do much of yet, and we would like to do more of, is perturbing the source, and that can also be very uncertain. And those two combined give you yet more uncertainty, more ability to quantify that uncertainty.
Any more questions from the floor or online? Great.
There's one online question from Nick Church. And the question is, have you considered using a CCN rather than a random forest for the air pollution modelling? This will allow grid cells around a point to influence the signal at that point.
I didn't catch all of that.
Sorry.
What's the name of the model?
CNN.
Well, I think they used regression type models, so random forest, gradient boosting. I don't know if that includes the CNN. But I didn't catch what the advantage of that would be.
It says this will allow grid cells around a point to influence the signal at that point.
Okay, so it would help mimic the infection. Is that the case?
If I may, so I think CNN is probably convolutional neural nets. So I guess the idea is that if you look at multiple grid cells at once, you can then learn a kind of convolution that looks at how the grid cells relate to one another spatially. Yeah?
I mean, as far as I know, they haven't done that. I mean, these were just quite small projects, so I think there's plenty of scope for improvement.
Thanks, Ben.